Hello, everyone. I'm Bill Gervasi. I'm the Principal Systems Architect for Nantero, and today I'm going to talk about memory expansion over CXL. So the agenda for today's talk, we're going to look at CXL expansion memory as a growing trend, but then we want to talk about openly what are some of the problems that customers are seeing with the potential adoption of CXL expansion memory. I'm going to give you a quick update on what's going on with Nantero NRAM, which is a persistent main memory. Then I want to talk about how persistent memory addresses these CXL problems that customers are raising. And then finally, I want to look at some of the system implementation aspects of what it takes to adopt persistent memory in today's data centers. So CXL is definitely on the rise. I'm sure that this conference is going to be filled with presentations about CXL and the emergence of what a revolutionary change it is in architecture and all that. It's kind of like the new Bluetooth for fabrics. It brought together all these warring factions for fabric buses for systems, but there's still a lot of work to be done, and that's what I want to look at. So let's focus on the memory expansion aspect. The assumption today is that CXL expansion is not going to replace DIMMs. Dual inline memory modules are still going to be attached directly to CPUs. That is not going away. However, the CXL expansion modules are going to be added to the system. However, you put DRAM in them, they're still going to be volatile. They will still lose data when power fails. One subtle point is that we're also envisioning that a lot of processors with a lot of cores in each processor are going to be sharing this CXL bus. And that's significant because what this is doing is it's raising the bar again for the randomness of accesses that are going to be going to the shared memory resource. Take a little history trip back. What has happened with memory capacity? Back in DDR1, we were working with 256 megabit memories, and we had 4 DIMMs per channel, so that gave us basically 4 gigabytes of total storage attached to a CPU. When we went to DDR2, we lost one of the DIMMs. We went from 4 DIMMs per channel down to 3 DIMMs per channel. However, we jumped up to the gigabit part, and we were able to put on a second memory controller, which allowed us to do a nice 6x improvement in performance and capacity. Now with DDR3, we lost another socket. We went down to 2 DIMMs per channel, but now we went up to the 4 gigabit part, so we still got a 4 gigabit by going to 3 memory channels. DDR4, we went to 4 channels, and we kept 2 DIMMs per channel, which was kind of cool. So this allowed us to get a nice jump up to 5x. DDR5, though, is the problem. In DDR5, we've dropped down to a single DIMM per channel, and the same capacity chip, 16 gigabit, that was available in DDR4 is now the mainstream part in DDR5 as well. So at best, we're seeing the same amount of memory by going to 8 channels. And maybe when the 32 gigabit chip finally comes out, we'll see a modest 2x improvement in memory capacity. So this is the dynamic that's driving the need to look at memory expansion. And so if you have these new applications like artificial intelligence and everything else that is demanding more and more memory space, and your DDR5 solutions aren't giving it to you, look to CXL to expand memory and get a bigger in-memory footprint. So what's not to love about CXL? It's a very pretty, elegant solution, runs on a standard PCIe bus, and then translates to a low overhead protocol. The thing that people have issues with, starting with the latency. Yes, this interface does add latency to every access, both reads and writes, and so that's going to be a concern. Related to that, but slightly different, is what is the performance of the memory itself? And I'm going to show you how those things are tied together, and the solutions to those are also tied together. The next is about power. PCIe is going up in frequency. It is continuing to burn a lot of power, and it's hard to put it into power management states. So that is a concern that customers have raised. And then what happens when that power goes away? Like I said, your memory, if you put DRAM out there, it's volatile. And when you lose power, you lose data. And then finally, what kind of capacity can you really get out of this kind of expansion? So let's take a look at all of those factors, because all of these may be slowing the adoption rate of CXL. CXL has a lot of buzz, but actual sales are what are important. So let's take a look at a quick update on what DDR5 is, NRAM is doing. This is Nantero's entry into this market with full DDR5 speed, non-volatility. It's scalable beyond the capacity of DRAMs, and it's lower power than DRAM. So let's see how this kind of solution is going to meet these end user requirements and address the concerns about introduction of CXL. You can see issue is still going to be real. We can't get rid of those SerDes. We can't get rid of the overhead moving the commands across the bus compared to direct access on a DRAM DIMM. However, CXL does do some good things, like it adds full duplex, meaning you can do reads and writes simultaneously, whereas on a DIMM, you have to choose between one or the other. And the third factor is caches and buffers can be put into CXL controllers, even in the type 3 form factor, which is the CXL.mem protocol. You can still do things like the buffering of writes, things like refreshes, and it can schedule around them. When you decouple across CXL, you don't have that. So now here's the best case situation. The host issues a read or a write command out to the CXL controller. The first thing the CXL controller is going to have to do is see if the DRAM is available or if it's in the process of doing a refresh. If it's not refreshing, no problem. You do the read or the write command, you move on, life is good. However, the devil is in the details. High percentage of the time, when you go out and make that read or write access, the DRAM is going to be refreshing. In this case, you have to wait quite a while and then finally complete the read or the write operation when the DRAM is done refreshing. So let's imagine now. Imagine that you have a persistent main memory like NRAM. If there were no refresh, let's see how that affects system performance. Now, for this analysis, I did assume that you're doing 2x refresh, another double refresh, and that's going to be your short-term solution to row hammer immunity and that sort of thing. So that's what everything's going to be normalized to. If you were to take NRAM, put it on a DIMM, and plug it into the same socket where DRAM was, what are you going to get? An 11% boost. And where does that come from? Straight from the elimination of refresh. But now we're going to take that CXL latency. Here I am making some assumptions about the amount of pipelining that you can do to hide a certain percentage of those accesses. And at that point, what I see is that you get 96% performance using NRAM on a CXL module compared to DRAM on a DIMM directly attached to the CPU. That is pretty close to an at-par relationship. The next level up, because this is going to be popular in the industry as well, if people put DRAMs onto CXL modules, the comparison again is going to be an 11% improvement for NRAM because of that elimination. And finally, everybody always asks about Optane, so let's put Optane into the mix. Now, this is a little harder because Optane is hard to model. It has a hypervisor, it has different block transfer sizes and onboard caching, but as close as we can come up with, we see that we'll have about a 65% performance advantage there as well. Now, what about power? Well, you have to be putting it in context. And the context that I chose was to put this in the context of a DDR5 LRDIMM, load-reduced DIMM. Now here, 6,400 megabits per second on the I/O interface. So in the time frame that CXL plus DRAM modules are going to be shipped, increase in power for the DRAM. And that's on the DIMM too, by the way. budget for the power for the register and the data buffers that are also to 6400. So they're going to be increasing in power. So I allocated 2 watts for those guys. So with 40 DIMMs on a maxed out LR DIMM, I come up with a 13 watt L module. The CXL module, it's going to have the same D decreasing 25%, blah, blah, blah. But the CXL controller is higher power than the register plus the data buffers by a factor of 3. It's about 6 watts, give or take. So in order to do an apples to apples comparison, we're going to have to do it in terms of the media capacity of the solution, meaning how much data are you getting for how much power you're spending. So let's look at the worst case situation. That's the E1.S. Put 20 chips on there. That's only half of the capacity of a DIMM. And you have the 6 watt overhead of the CXL controller. So this comes out to about 56% efficiency. In other words, efficiency measured as the total memory capacity for the number of watts that you're spending. The larger form factor, the E3.S, it can fit 40 chips in a fairly easily. And now you get a better gigabytes per watt, coming in at around 77% efficiency. But with careful design, you can fit 80 chips onto a CXL module. Now you've gotten a pretty decent mix because you're fitting 2 DIMMs worth of data in a single CXL module. And now you're up to 92% efficiency compared to the 2 DIMM solution. Now I'm going to take a little side trip, which is into the nature of non-volatile memory. And this has to do with something called activation. And it's a little nerdy, but I think you're going to get the main message here. When a DRAM reads a row out of the core, it erases that. Those capacitors discharge onto the bit lines to fill up the sense amplifiers. Now maybe you come along and you do a read. Well, you do the read from the sense amps, not from the core, because the core is invalid now. And so you have to have an operation called pre-charge. And the function of pre-charge is to take that data, write it back into the core. You have to do this even though read doesn't modify the data whatsoever. In the case of writes, you have an even worse situation. Now you write the data out and you have to do a pre-charge to get it back into the core so that the core is valid again. Now this happens on every read and every write. And now what I said about multiple processors, each multi-core sharing this memory resource, the accesses to CXL memory modules are going to be extremely random, meaning they're going to want to run closed page, activate, read, pre, 8 kilobits of data movement for every 64 bits of actual data usage. It's not very efficient. Now let's look at what happens. Activation does not destroy the core. It's still valid even after you read it out to the sense amps. When you read the data from the sense amplifiers, you're just done with that operation. So you've done a 1 kilobyte transfer from the core out to the sense amps. You do on writes, it's kind of similar. You're going to read more consistent. And if you want to support any kind of open page access, you also write it to the sense amps. That's kind of an optional thing. But the key message there is that instead of having to do 8 kilobits of data movement, you can do only 64 bits of data movement, further reducing power. So let's look at the effects of all this. This model here talks about a typical server, which is 2/3 read, 1/3 write. And now, if you're not going to do refresh, I even threw in an extra read and a write during those refresh times. So while you're delivering 11% more data at the same clock frequency, you're still coming in with a 21% power reduction. Put together, that means you have a 34% better throughput per watt than a DRAM. So now let's translate that to the module level. At the module level, two DDR5 DIMMs are normalized to 100%. If you put DDR5 SDRAMs into a CXL module, now you've gotten a significantly higher power envelope. And so you've bumped up about 8% on power. With NRAM, 2 DIMMs worth fits into a single 80 package CXL module. And with that 21% power reduction, you can see that the power numbers come in significantly below 2 DIMMs worth of data as well. And finally, because this is persistent memory, you can start reducing your usage of the SSD and save power that way as well. So let's address the volatility question. You could just let your data die, and this is what you're doing today. You're using the SSD to do checkpointing so that when power fails, you can lose data without losing the state of the machine. You can add supercapacitors, and this is what NVDIMM-Ns do. It's also what a future generation of CXL modules can do, which is when power fails, you copy the contents of DRAM to flash. When power is restored, you bring it back. However, with NRAM, you just put the NRAM module in there, and it is inherently non-volatile. So we're going to be coming in with a 16 gigabit part, soon to be followed by a 32 gigabit part. The capacity analysis will be based on this. So we look at doing a CXL controller with 2 DDR ports. That gives you 4 sub-channels running at 25.62 gigabyte per second throughput on a by 8 CXL bus. So that's how you fit 80 chips. And finally, here's in expansion, going anywhere from 64 gigabytes to 2 terabytes per module in the E3.S form factor. And this is more for the commodity space. So you get 32 gigabytes at the high end of non-volatile memory. And to enable this, we need the software work to be done. DAX is for allowing people to go from mounting persistent memory as a drive, as a RAM drive, and then eventually going to direct access mode. So that roadmap is still intact, but it's really not where the end game is. The end game is that we really want to get to the point where we have persistent main memory throughout, where we can boot from CXL. When power fails, we can restart directly from CXL. And the model for this is something called the baby spec that's out of JEDEC. And what we would do is eliminate the energy back portion of this baby spec and be able to restore directly from a persistent memory image. So this old paradigm of checkpointing, every time you get to a critical point in your application, copying that data from SDRAM out to the flash drive, that can go away because we have a new paradigm where you just leave the data in place and you just run. So someday we're going to reach that holy grail of when we can actually do instant reboot from a system, and non-volatile main memory is the thing that's going to make that possible. So we're looking at CXL for memory expansion has some valid concerns, but I think persistent memory is going to show that it can solve those problems and make customers comfortable with investing in CXL. Nantero NRAM is a DDR5 class persistent memory, and the DAX model is going to help people move over to the support of persistent memory, but that holy grail is still going to be end-to-end data persistent and instant on. And with that, I'd like to thank you for your time, take questions, and remember to fill in the feedback on these sessions.